Let us next consider my first example using this disk method. Consider a semicircle whose radius r and whose center is at the origin. Now that r is merely constant. Let's take this region, rotate it about the x-axis, and compute the corresponding volume of that solid at revolution. Now to do that, since I'm rotating about the x-axis, I suppose my rectangles are going to be vertical. The corresponding disk is imagined as such. And so, setting up my interval, I recall the volume can be interpreted as pi times an interval from here to here of my radius squared times my thickness. Now, in setting up an interval, I do not initially worry about bounds of integration. I do not initially worry about the radius because they depend on what variable I'm integrating with respect to. So with all these techniques of computing volume that I have for you, I always look at the thickness first because it does identify the variable integration. Now, when you take a peek at that rectangle, notice how it has a small change, a small quantity for the horizontal dimension. That's a small change in the x direction. That delta x is going to turn into dx when I take the limit of the Riemann sum, and here is the limit of the Riemann sum in integral form. So first things first, I have an integration process with respect to that variable. All I need to, I shouldn't say all, but next I need to worry about the radius. That's what's being squared. But the radius is nothing more than the y value of the curve. And the y value of the curve can be interpreted as the square root of this. And I think the x values are ranging from negative r to r. And if you're not sick of me saying this already, gosh, I'm just too tired and lazy to do this. So if you don't mind, I'm going to exploit symmetry. We can now anti-differentiate. I apologize for running out of board space. So everybody, look what we just did. We've accomplished the task of deriving out of thin air the formula for computing the volume of a sphere whose radius is fixed at r.